Good morning, students. In the last class, we had a discussion about inversion. What is inversion? What is the purpose of inversion? And in detail with examples, the inversions of 4-bar chain and single slider crank chain has been discussed. If I recall the inversions of 4-bar chain, only 3 inversions are possible, and the single slider crank chain, in which we have discussed about all the 4 inversions. Now, moving on to the third type of kinematic chain, that is double slider crank chain. As shown in the figure, it consists of 4 links, namely slotted plate, sliders and connecting link. All these links forms 4 kinematic pairs. Out of 4 pairs, 2 are turning pairs and the other 2 are sliding pairs. The links are named as 1, 2, 3 and 4, in which 1 and 2 and 1 and 4 are sliding pairs, 2 and 4 and 3 and 4 are turning pairs. This is a double slider crank chain, in which one is slotted plate and slider, which is 2 in numbers, and connecting link. Now, moving on to the inversions of double slider crank chain. The inversions of a double slider crank chain are: first inversion. The first inversion, here it is obtained by fixing the slotted plate of a double slider crank chain, for which we can take the elliptical trammel as example. Elliptical trammel is one of the inversion of a double slider crank chain, which is obtained by fixing the slotted plate of a double slider crank chain. It is used, elliptical trammel is used in automatic tool changer in a machining. Also, it is used for inscribing the ellipse. It consists of 2 sliders which are confined to perpendicular channels. In the figure, the 2 sliders are named as 2 and 3. So, elliptical trammel consists of 2 sliders. Here they named as 2 and 3, which are confined to perpendicular channels, and a connecting link, that is named as 4, link 4, which is attached to the sliders by pivots at fixed position along the connecting link. When the sliders moves back and forth, each along its channel, the end of the connecting link traces an elliptical path. Now let us consider a point P, which is shown in figure, on a straight line between A and B. It makes an angle theta with respect to x-axis, and let us take the coordinates of the point P are x and y. So obviously the point P is also making an angle theta because of the corresponding angle. Now if I consider the triangle APC, from the triangle APC I can find cos theta. What is cos theta? In the triangle APC, it is adjacent side by hypotenuse, that is equal to x divided by AP. Similarly, if I consider the triangle PBD, because these two triangles are similar triangles, that is triangle APC, from which I calculated cos theta, which is equal to x by AP. That I called it as equation 1. Similarly, from the triangle PBD, let us find out the sin theta. So sin theta is equal to opposite side by hypotenuse, that is equal to y by BP. So cos theta is equal to x by AP, that is equation 1. Sin theta is equal to y by BP, that is equation 2. Now squaring and adding equations 1 and 2, it is x square by AP square plus y square by BP square. I am just squaring and adding both sides of the equations 1 and 2. If I add the right hand side of both the equations after squaring, it is x square by AP square plus y square by BP square, which is equal to squaring and adding of left hand side of the two equations. Then it will be cos square theta plus sin square theta. Thereby x square by AP square plus y square by BP square is equal to 1, because sin square theta plus cos square theta is equal to 1, where this is known as the equation of ellipse. Suppose if the point P is considered exactly in the middle of the line AB, such that AP is equal to BP, then if I substitute in the ellipse equation x square by AP square plus y square by BP square is equal to 1. It is the equation of ellipse. Now the point P has been considered exactly in the middle of the line AB, so that AP is equal to BP. Therefore, wherever you find BP, in place of it, replace it by AP, because AP is equal to BP if the point P is exactly in the middle of the line AB. So thereby, by substituting in place of BP by AP square in ellipse equation, then I am going to get x square plus y square is equal to AP square, which is said to be the equation of a circle. Like that, as I said, elliptical triangle is used in order to inscribe the ellipse. Using the equation of ellipse, one can trace an ellipse using the elliptical triangle. Instead of the point P at anywhere on the line AB, if it is considered exactly in the middle of the line AB, it will trace as a circle. So this is about the first inversion of a double slider crank chain. I am once again recalling, it is the inversion. Elliptical triangle is one of the inversion which is obtained by fixing the slotted plate of a double slider crank chain. Mainly it is used in order to inscribe the ellipse, and as well it is used as a automatic tool changer in machining. Now let us go to the second inversion. In second inversion is obtained by fixing one of the slider. So here there are two sliders in a double slider crank chain. By fixing either the slider 2 or slider 3 in the diagram of of a double slider crank chain, one can get the second inversion of a double slider crank chain, which is obtained by fixing any one of the slider in a double slider crank chain, for which the Scotch yoke mechanism is an example. Scotch yoke mechanism is one of the inversions of a double slider crank chain which can be obtained by fixing any one of the slider. This mechanism is used to convert rotary motion into reciprocating motion or vice versa. So as you can see in the figure, there is a link 1 which is pivoted at point O, and slider is the link 3, crank is the link 2, and frame is the link 4. Now by fixing one of the slider, one can get a mechanism known as Scotch yoke mechanism, which is mainly used in order to convert the rotary motion into reciprocating motion or vice versa. So this mechanism one can see in front of our workshop lab the machine known as power hexa. So in front of the machine workshop, when one can see the power hexa in which the Scotch yoke mechanism can be observed and it's working. When the crank rotates about to the point O, then the frame consists of piston inside a large cylinder reciprocates and the fixed link 1 guides the frame. This is about a second inversion. Then the third inversion of the double slider crank chain, in which by fixing one of the element, that is connecting link, by fixing the connecting link of a double slider crank chain, one can get a mechanism known as a Oldham's coupling. As shown in the figure, it is used for connecting two parallel shafts. One can see the two parallel shaft which is written in the figure as a driving shaft and driven shaft. These two parallel shafts will be connected whenever the axis of both of them are at a small distance apart. Means the axis of the driving shaft and the axis of the driven shaft are far away through a certain distance, or whenever the axis of the driving and driven shafts are at a small distance apart, one can use the Oldham's coupling in order to transmit a power in between a driving shaft to the driven shaft. The shafts are coupled in such a way that if one shaft rotates, the other shaft rotates at the same speed. It consists of, in addition to driving shaft and driven shaft, it consists of, one is supporting frame, which I named it as link 2, and there are two flanges, flange which is link 1 and as well as one more flange which is link 3. In between there is an intermediate piece, or it is also known as intermediate flange, which is named as link 4. The two flanges, each having a rectangular recess, are keyed one on each shaft. An intermediate disc or the intermediate piece having tongs at right angles on opposite sides is placed in between the flanges. When flange, that is link 1, turns, the intermediate piece, that is link 4, must turn through the same angle, and whatever the angle the intermediate piece turns through, the flange, that is link 3, must turns through the same angle. So in this way the power can be transmitted in between the driving shaft and the driven shaft. So this Oldham's coupling or this kind of mechanism is used in wafer polishing apparatus, German equatorial telescopic mount. So these are the inversions of a double slider crank chain. So The points to be remembered in a double slider crank chain, there are 4 links, out of which one is slotted plate, and link 2 and 3 are the 2 sliders, and link 4 is the connecting rod. By fixing the slotted plate, I can get one inversion, which is a elliptical trammel. By fixing any one of the slider, that is either link 2 or 3, we can get one more inversion, that is Scotch yoke mechanism. By fixing the connecting link, that is link 4 of a double slider crank chain, one can get a third inversion, which is a Oldham's coupling. Therefore, after knowing all the inversions, so first inversion, elliptical trammel, second inversion, Scotch yoke mechanism, third inversion, Oldham's coupling. Now, if I recall, if I just summarize about the inversions of a kinematic chain, first is 4-bar chain. Only 3 inversions are possible. In the same way, in case of a double slider crank chain, as the link 2 and link 3 are the same elements, means both are sliders. Therefore, in double slider crank chain also, one can get the 3 inversions as in the case of a 4-bar chain. So, 3 inversions in a 4-bar chain, 3 inversions also in a double slider crank chain, and only the 4 inversions are possible in case of a single slider crank chain. Now, let us know what is Grahoff's law. The Grahoff's law states that for a planar 4-bar linkage, the sum of the shortest and the longest link length cannot be greater than the sum of the remaining 2 link lengths if there is a continuous relative motion between the 2 members. This is the statement of a Grahoff's law. What the Grahoff's law says? In a 4-bar linkage, the sum of the shortest and longest link length cannot be greater than the sum of the remaining 2 link lengths, provided if there is a continuous relative motion between the 2 members. For example, if I consider a 4-bar chain which is shown in the figure, link 1 is a frame, link 2 is a crank or a driver, link 3 is a coupler or a connecting rod, link 4 is a lever or a rocker. If I take a 4-bar chain, in 4-bar chain, if none of the links makes a complete revolution, then it is not useful in practical applications. Hence, it is necessary that one of the link must be a revolving link. Students, anyone can say which is the link in a 4-bar chain makes a complete revolution? That is crank or the link 2 in a 4-bar chain. So, using Grahoff's law, if any one of the link in a kinematic chain can be examined. So, the purpose of Grahoff's law is to examine or to verify that any one of the link can be explained, because in order to use any mechanism for any practical applications, one of the link in a mechanism must be a revolving link. Therefore, using Grahoff's law, one can examine that whether one of the link is revolving or not. Now, let us take L suffix P is the length of the frame, L suffix S is the length of the crank, L suffix L is the length of the coupler, and L suffix Q is the length of the lever or the rocker. According to the Grahoff's law, if L2 is the length of the shortest and L3 is the length of the longest link, then according to the Grahoff's law, what the Grahoff's law says? Sum of the shortest and longest link lengths, that is LS plus LL, cannot be greater than, therefore less than or equal to sum of the remaining links in a 4-bar chain, that is LP plus LQ. Again I am repeating, according to the Grahoff's law, in a 4-bar chain, LS is the length of the shortest link and LL is the length of the longest link, then sum of the shortest and the longest link, that is LS plus LL, less than or equal to LP plus LQ. If the equation 1 is not satisfied, then no link will make a complete revolution relative to any other link, and hence the chain is called as non-Grahoff chain. Suppose if LS plus LL is less than or equal to LP plus LQ, then the given kinematic chain is called as a Grahoff chain. If the equation 1 is not satisfied, then it is called as, or the given chain is called as a non-Grahoff chain. Like that, one can identify whether the given kinematic chain is a Grahoff chain or non-Grahoff chain based on the Grahoff's law. If LS plus LL is less than or equal to LP plus LQ, then it is a Grahoff chain. If it is not satisfied, means if LS plus LL is not less than or equal to LP plus LQ, then it is a non-Grahoff chain. Now let us take some simple examples. Problem number 1. Figure shows the 4 link mechanisms. I gave 4 link mechanisms of totally 4, in which the figure indicates the dimensions in standard units of length. Indicate the type of each mechanism, whether crank rocker or a double crank or a double rocker. Now, what I said after just giving the statement of the Grahoff's law, in the given kinematic chain, a shortest link is fixed, and if it satisfies the equation 1, then the mechanism is drag link mechanism or double crank chain mechanism. If any one of the 2 links adjacent to the shortest link is fixed, and if it satisfies the equation 1, then the mechanism is behaving as a crank lever or a crank rocker mechanism. If the link opposite to the shortest link in a 4-bar chain is fixed, and if it fulfills the Grahoff's law, then the given chain can be used as a double lever or a double rocker mechanism. Like that, these are the 3 conditions. Not only we have to decide that whether it is going to satisfy the equation 1 or not of the Grahoff's law, one should also find in the given kinematic chain a shortest link is fixed, and if it fulfills the equation 1 of a Grahoff's law, then the given kinematic chain can be used, or it is behaving as a drag link or double crank chain mechanism. If any one of the 2 links adjacent to the shortest link, that is either link 1 or link 3 in the figure, because link 2 is the shortest. So if any one of the link adjacent to the shortest link, that is link 1 or link 3 is fixed, and if it satisfies the Grahoff's law, then it is a crank lever or a crank rocker mechanism. And similarly, if the link opposite to the shortest link, that is link 4, is fixed and it satisfies the equation 1 of Grahoff's law, then it is a double lever or a double rocker mechanism. Now, in the example, if I take the first one, it is a 4-link mechanism with the dimensions of each link is 5, 8, 9, 10. Now, in this mechanism, length of the shortest link is 5 and the longest link is 10. Therefore, LS plus LL is equal to 5 plus 10, that is equal to 15. Similarly, the sum of the remaining links, that is 8 plus 9, which is 17. Hence, 15 is less than 17. Hence, the chain is a Grahoff chain because it satisfies the Grahoff's law. And in this mechanism or in this chain, shortest link is fixed. Therefore, it is a double crank mechanism or drag link mechanism. Similarly, in the second one, the dimensions are 6, 9, 10 and 11. Here the shortest link is 6 and longest link is 11. Therefore, sum of the shortest and longest is 6 plus 11, which is equal to 17. And the sum of the remaining links are 9 plus 10, which is 19. So, 17 is less than 19. Therefore, the given kinematic chain satisfies the Grahoff's law. And here the link, one of the link adjacent to the shortest link, shortest link is 6. So, adjacent to the shortest link, any one of the link is fixed, then it is a crank rocker or a crank lever mechanism. Now, if I take the third example in which the dimensions of the 4 links are 8, 10, 12 and 15. Here the shortest link is 8 and the longest link is 15. Therefore, according to the Grahoff's law, sum of the shortest and longest link lengths are 8 plus 15, which is equal to 23. And the sum of the remaining links are 10 plus 12, which is 22. So, 23 is greater than 22. Hence, it is not satisfying the Grahoff's law. Therefore, the chain is said to be rock chain. Then the fourth example in which the dimensions of the 4 links are 5, 8, 9 and 10. Now, if I apply the Grahoff's law to this, sum of the shortest and longest, that is 5 plus 10, which is equal to 15. Then sum of the remaining links are 8 plus 9, which is 17. Hence, 15 is less than 17. Therefore, the given kinematic chain satisfies the Grahoff's law, and here the link opposite to the shortest link is fixed. Hence, it is a double lever or a double rocker mechanism. Then the one more example, a 4-bar mechanism has links of lengths 150 mm, 250 mm, 300 mm and a frame which is L0 mm. Find the range of L0 if the mechanism has to work as double crank mechanism and crank rocker mechanism. So, you must find in this example, it is a 4-bar mechanism where the dimensions of the 3 links are given. One is 150, other one is 250 mm and the last one is 300 mm. Among 4 links, 3 link dimensions are given. You have to find out the length of the frame, that is L0, in between what values the L0 should lie if at all this 4-bar mechanism should act as a double crank mechanism, that is our case 1, and if it should act as a crank rocker or a crank lever mechanism, that is our case 2. Now, let us take the case 1. This 4-bar mechanism to be act as a double crank mechanism, the condition is the shortest link of this 4-bar mechanism must be fixed. Now, let us take the Grahoff's law or the Grahoff's equation. Ls plus Ll is equal to Lp plus Lq. Now, the value of L0 which I should find may be a shortest or may not be a shortest. Therefore, one cannot take. So, may be a shortest. The range of L naught which I should find may be a shortest link. Therefore, so Ls is equal to L naught plus the length of the longest link is 300. So, L naught plus 300, which is equal to sum of the remaining links, sum of the lengths of the remaining links, that is 150 plus 250. Then L naught is less than or equal to 150 plus 250. Take this 300 to the right hand side, then it becomes minus 300. Hence, L naught should be less than or equal to 100 mm. So, therefore, the value of L naught should be less than or equal to 100 mm, so that this given 4-bar mechanism can be act or behave as a double crank mechanism. Then the second case, that is when this 4-bar mechanism can act or can behave as a crank rocker or a crank lever mechanism. Now, first of all, one should understand, in order to behave any given kinematic chain as a crank rocker or a crank lever mechanism, the condition is the link opposite to the shortest link is to be fixed. Link opposite to the shortest link is to be fixed. Now, among the 4 links, the shortest link is 150 mm. Therefore, we have to take here, for this case, length of the shortest link is equal to directly 150 mm, because one of the link opposite to the shortest link should be fixed. So, now if Ls is equal to 150 mm, the L naught, the link which is opposite to the shortest link, may be a longest link or may not be a longest link. Suppose if L naught is the longest link, then Ls plus Ll is less than or equal to Lp plus Lq. Accordingly, we get L naught is less than or equal to 400. Suppose if the L naught, that is the length of the frame, may not be a longest length, then 150 plus 300 will be the sum of the shortest and longest length, which is less than or equal to 250 plus L naught, from which one can get L naught should be greater than or equal to 200. So, therefore, the range of L naught value in order to become this 4-bar mechanism as a crank rocker mechanism or a crank lever mechanism is L naught should be in between 200 to 400. Like that, one can find out degrees of freedom. So, the degrees of freedom. What is degrees of freedom? It is the number of independent coordinates required to describe the position of a body in a space. So, the number of independent coordinates in order to specify the configuration of a body is known as a degrees of freedom. Let us consider a body in a space which is shown in the figure. The body which is in a space can have 6 degrees of freedom, that is linear positions along x, y and z, which are shown by the arrows, and rotational or angular positions with respect to x, y and z axis, which are shown with the curvature arrows like this. Totally 3 translational and 3 rotational. Altogether 6 degrees of freedom whenever the body is in a space. So, planar mechanism. What is a planar mechanism? When all the links of a mechanism have plane motion, then it is called as a planar mechanism. All the links in the planar mechanism move in planes parallel to the reference plane. Now, let us take degrees of freedom or a movability or a mobility. So, how to find the degrees of freedom, or how to find movability, or how to find the mobility for a planar mechanism. So, now for that, let us consider which is shown in the figure to determine the degrees of freedom for a planar mechanism. Let us consider two links 1 and 2 in xy plane as shown in the figure. Link 1 is fixed along x-axis, whereas link 2 is moving in a plane. But at any time, the position of the link 2, that is point A of link 2, can be completely specified by three variables, that is coordinates x and y and its inclination theta of the link 2 with x-axis. Therefore, the three independent variables, that is two translational along x and y and one rotation, that is theta, are necessary to locate the link 2 in xy plane. Therefore, anyhow the link 1 is fixed, which cannot have any mobility or degrees of freedom. The link 2, now one can say that link 2 is having a 3 degrees of freedom. But if the point A is joined by a pin to point B on a fixed link 1, then the two independent variables, that is x and y coordinates, are fixed. What I am doing here, when link 1 and link 2 are separate, anyhow link 1 is fixed, no mobility or no degrees of freedom. Link 2, as it is lying in the xy plane, which is not fixed, therefore the point A of a link 2 will have 3 degrees of freedom, or it can move in 3 directions. It may translate along x, or it may translate along y, or it may take rotation. Therefore, link 2 is having 3 degrees of freedom. Now what I am doing, I am just joining the point A by a pin to the point B on a fixed link. Then the two independent variables, that is x and y, are going to be fixed. Therefore, the position of the link 2 in a xy plane can be determined with only one variable, that is theta, because translational coordinates have been constrained or restricted by connecting the point A to the point B. Thereby only configuration of the link 2 or the position of the link 2 can be stated or determined with only one variable, that is theta. Hence, in this position, link 2 is having now only 1 degrees of freedom, that is theta, which is angular or rotational. Therefore, from this one can conclude that 2 degrees of freedom are lost. We have lost the 2 degrees of freedom at every pin or hinge joint of any link with the fixed link. So, if I connect any link with either a pin joint or a hinge joint to any fixed link, then we are going to lose the 2 degrees of freedom. Only it will have 1 degrees of freedom. Like that one can give the conclusion about the degrees of freedom in case of a planar mechanism. Now, let us find degrees of freedom or mobility for some of the mechanisms. Now, how to find? The 2 criteria are available to find the degrees of freedom for a planar mechanism. One is Grubler's criteria and the other is Kurzbach criteria. Now, according to them, the degrees of freedom can be obtained by using one recurrence relation, which is given by F is equal to 3 into n minus 1 minus 2p1 minus p2, in which F is known as mobility or number of degrees of freedom. P1 n is equal to number of links including the fixed link. P1 is equal to number of binary joints or lower pairs with single degree of freedom. P2 is equal to number of higher pairs or number of joints with 2 degrees of freedom. So now on applying this equation to find degrees of freedom for any mechanism, one should keep in mind the three conditions. After finding the mobility or the number of degrees of freedom or simply F, because F stands for number of degrees of freedom. If F is greater than 0, then the device is a mechanism with F degrees of freedom or the mechanism with constrained motion. If I calculate F which is greater than 0, then the given chain or the given mechanism is having a constrained motion with that many number of degrees of freedom. If number of degrees of freedom, that is F, is equal to 0, then it is called as statically determinate structure. If F is less than 0, then it is said to be statically indeterminate structure. Like that, use equation to find out the degrees of freedom. Later, based on the value of F, one can decide maybe F is greater than 0, then the mechanism is having a constrained motion with F degrees of freedom. If F is equal to 0, then it is said to be a statically determinate structure. If F is less than 0, the device is a statically indeterminate structure. Now let us take simple examples. Determine the mobility of the mechanism which is given below. It is a 3-link mechanism which is named as 1, 2, 3, in which number of links, that is n, which is equal to 3 links, and number of binary joints are 3, and number of higher pairs, number of lower pairs is equal to 3, and number of higher pairs is equal to 0. So that is n is equal to 3, P1 is equal to 3, P2 is equal to 3. If I substitute these values in the equation of degrees of freedom, I will get F is equal to 0. Here F is equal to 0, hence the mechanism is said to be statically determinate structure. Then taking the another example, it is a 4-bar mechanism in which there are 4 links, that is n is equal to 4, and number of binary joints or number of lower pairs, that is P1, is equal to 4, and number of higher pairs, that is P2, is equal to 0. So if I substitute, I am going to get F is equal to 1. So hence F which is equal to 1 here is greater than 0, hence the mechanism is having a constrained motion with 1 degree of freedom because F is equal to 1. Similarly, if I take the next one, it is a 5-link mechanism. So therefore, number of links is equal to 5, number of binary joints or number of lower pairs, that is P1 is equal to 5, and number of higher pairs is equal to 0. If I substitute these values in the equation, I am going to get F is equal to 2. It means F is equal to 2. It means it is greater than 0, as F is equal to 2, which is greater than 0. Hence the mechanism has constrained motion with how many number of degrees of freedom? With 2 degrees of freedom. Similarly, if I take the next example in which one can identify totally 6 links. Link 1 which is fixed, 2, 3, 4, and similarly opposite corners are also joined by 2 more links. They are 5 and 6. So totally in this example, number of links is equal to 6. Number of lower pairs one can calculate, then it will be 8. So the number of lower pairs is equal to 8, which can be calculated by using n plus L minus 1. That is, number of links is equal to 6 and number of loops. Here this is 1, 2, 3, 4. Totally 4 loops. So 6 plus 4 minus 1. 6 plus 3. 3 loops and 1. 6 links, 3 loops and 6 plus 3 minus 1. Therefore, number of binary joints is equal to 8. Or in other way, so A is equal to 2, B is equal to 2, C is equal to 2, D is equal to 2. So at each point, at points A, B, C, D, so 2 links are connected. So therefore, all these joints are ternary joints. Therefore, ternary joints to be taken as 2 binary joints. Thereby, the number of binary joints is equal to 8. Or by using a loop method, one can calculate the number of lower pairs, which is equal to 6 plus 3 minus 1. N is equal to 6, which is the number of links, and number of loops is equal to here 3. Thereby, number of lower pairs or number of binary joints is equal to 8. And here there are no lower pairs, higher pairs. Therefore, number of higher pairs, that is P2, is equal to 0. If I substitute in the equation, I am going to get F is equal to minus 1, which is less than 0. Hence, the given mechanism is said to be statically indeterminate structure. Next, moving on to a slider crank mechanism, which is shown here. There are 4 links and 4 binary joints or 4 lower pairs, and number of higher pairs is equal to 0. If I substitute F is equal to 1, so as F is equal to 1, which is greater than 0, hence the mechanism is having a constrained motion with a single degree of freedom. Similarly, if I take the next example, in this, number of links is equal to 6 and number of lower pairs or number of joints is equal to n plus L minus 1, where n is equal to number of links and the number of loops. Here all the links are forming the 2 loops. Therefore, 6 plus 2 minus 1, which is equal to 7. Number of higher pairs is equal to 0. If I substitute, then I am going to get F is equal to 1, which is greater than 0. Hence, once again, this mechanism is also having a constrained motion with 1 degree of freedom. Next, if I take the next example, it is June 2019 example, in which number of links are equal to 5 and number of binary joints is equal to 2 and number of ternary joints is equal to 2. Therefore, total number of binary joints are equal to 6, or number of lower pairs is equal to n plus L minus 1. So, 5 plus 2 loops, that is 7, 7 minus 1 is 6. Like that also one can calculate P1 value. The number of higher pairs, that is P2, is equal to 0 on substituting n, P1, P2 in this equation. I am going to get F is equal to 0. Hence, the mechanism is statically determinate structure. Next, taking this example in which there are, one is a fixed link, 2, 3, 4 and 5. So, total number of links in this example is equal to 5. And total number of lower pairs is equal to 5. How? Number of links is equal to 5 and it is 1 loop. Right. So, 5 plus 1 minus 1. Therefore, total number of lower pairs, that is nothing but number of binary joints, which is P1, that is equal to 5. And number of higher pairs is equal to 0. On substituting all these values, I am going to get F is equal to 2, which is greater than 0. Therefore, mechanism is having a constrained motion with 2 degrees of freedom. Similarly, if I take the next example, here number of links are equal to 6, in which one is a ternary joint, that is link 6 is a ternary joint. So number of links is equal to 6 and number of lower pairs is equal to 7. And number of higher pairs is equal to 0, thereby on substituting all the values. How? Here number of links are 6 and number of lower pairs or number of joints. Like this I can calculate, or simply n plus L minus 1. N means 6. L is equal to number of loops. Here this is one loop, this is one loop. So total loops are equal to 2. And 6 plus 2 is 8. 8 minus 1 is 7. Therefore, number of lower pairs, that is P1 is equal to 7 and number of higher pairs is equal to 0. Thereby, F is equal to 1, which is greater than 0. Therefore, this is a mechanism having constrained motion with 1 degree of freedom. Similarly, if I calculate next example, in this example, so number of links are equal to 11, which are named as 1, 2, 3 and so on to till 11, and the number of lower pairs, that is P1, is equal to 15, is equal to 15, that is 11 plus 5. 11 is the number of links and number of loops is equal to 1, 2, 3, 4, 5. So total number of loops are equal to 5. So 11 plus 5 is 16. 16 minus 1 is 15. Therefore, number of lower pairs P1 is equal to 15 and number of higher pairs P2 is equal to 0. So on substituting n P1 P2 in this equation, I am going to get F is equal to 0. So as F is equal to 0, therefore mechanism is said to be a statically determinate structure. Next, taking the next example, here I gave the two figures, one or the other same. So in this mechanism, there is a roller which is carried at the end of the output link, which can be rotated without carrying any motion in the rest of the mechanism. Hence, the roller is a link with redundant degrees of freedom. Right. Suppose if the roller is welded to the output link, then one should find the number of links. Here it is equal to 3 and number of lower pairs is equal to 2 and number of higher pairs is equal to 1. On substituting F is equal to 1, which is greater than 0. So the mechanism is a constrained motion having 1 degree of freedom. Just moving on to the next example, in which here the number of links are equal to 5. 1, 2, 3, 4 and 5. And in problem number 8, so number of lower pairs is equal to 5 because five and one loop. So 5 plus 1 minus 1. Therefore, number of lower pairs or number of binary joints, that is P1 is equal to 5. And here there are no higher pairs at all. Sorry, there is one higher pair. So one higher pair means, I will recall now, higher pair is the one in which either there is a point or a line contact. Here in between 4 and 5, so there is a point contact, therefore 4 and 5 link forms one higher pair. So number of higher pairs is equal to 1. On substituting, I will get F is equal to 1. As F is equal to 1 is greater than 0, hence the mechanism is a constrained motion with a single degree of freedom. Next, taking the problem number 9, now in which there are totally 14 links which are named as 1, 2, 3 and so on till 14. So now the number of links is equal to 14 and number of lower pairs is equal to 13 plus 6 minus 1. Here, because one of the link, that is link 4 is a higher pair. 3 and 4 are forming a higher pair because there are rollers in the link 4. Therefore, so there is a point or a line contact. So hence 3 and 4 is forming a higher pair. Therefore, number of higher pairs in this example is 1 and the number of lower pairs n plus l minus 1. One thing I would like to point out here, whenever there is a higher pair is found in any one of the given mechanism, number of higher pairs which I told you to calculate using n plus l minus 1. That n, strictly speaking, it is number of links which includes the fixed link. But if there is a higher pair, if at all any two links are forming a higher pair, then the number of links n is equal to be taken as total number of links minus number of higher pairs. That gives the value of n while calculating the number of lower pairs. That is why here instead of 14 I took 13 because 1 there is a higher pair. So 13 plus number of loops are totally 6 here. 13 plus 6 minus 1 which is equal to 18. And number of higher pairs is equal to 1. On substituting we will get f is equal to 2 which is greater than 0. Hence this mechanism is also having a constrained motion with 2 degrees of freedom. Then the problem number 10 in which number of links are 4. 1, 2, 3, 4. So n is equal to 4 and number of lower pairs is equal to, here there are no higher pairs at all. Therefore totally n is equal to 4 only, plus number of loops is equal to 2. So then 4 plus 2 minus 1 is equal to 5. Number of higher pairs is equal to 0. On substituting these values in equation, I will get f is equal to minus 1 which is less than 0. Therefore the given mechanism in problem number 10 is statically indeterminate structure. Then problem number 11 in which number of links are 5 and number of lower pairs is equal to number of links. Now it is 4 because 1 and 5 is forming a higher pair. Therefore n is less than, n is 5 minus 1. Then it becomes 4. 4 plus 1 which is 1 loop minus 1. Therefore number of lower pairs is equal to 4 and number of higher pairs is equal to 1, as I said already, 1 and 5. So on substituting the values I am going to get number of degrees of freedom, that is f, which is equal to 3 and it is greater than 0. Hence the mechanism is having once again a constrained motion with 3 degrees of freedom. With 3 degrees of freedom, like that. Next is problem number 12. By looking at the figure, we all can identify it is a elliptical trammel, or you can also call it as a double slider crank chain mechanism in which there are 4 links. Therefore n is equal to 4 and the number of lower pairs, that is P1, which is equal to n plus l minus 1. So here there are no higher pairs at all, hence n is equal to 4 only, plus number of loops is equal to 1. So 4 plus 1 minus 1, once again number of lower pairs, that is P1, is equal to 4 and number of higher pairs P2, that is equal to 0. On substituting the values in equation of degrees of freedom, I am going to get or f is equal to 1 which is greater than 0. Hence the mechanism is said to be a constrained motion with 1 degree of freedom. Then problem number 13, number of links is equal to 4. By looking at this, one can identify it is a mini drafter where having the number of links is equal to 4, which are named as 1, 2, 3 and 4, and number of lower pairs. Here also there are no lower pairs, all pairs are no higher pairs, all pairs are lower pairs only, therefore n is equal to 4 and number of loops L is equal to 1 minus 1. Then number of lower pairs, that is P1 is equal to 4 and higher pairs P2 is equal to 0. Then by calculating degrees of freedom, we get F is equal to 1, which is greater than 0. Hence, the mechanism is said to be having a constrained motion with 1 degrees of freedom. Then 14th one, number of links. Here it is equal to 3, which are named as link 1, which is a fixed link. Then 2 and 3 are the rollers which are in contact. Here 2 and 3 are in contact with each other. So 2 and 3 is forming a higher pair. Therefore, here number of higher pairs is equal to 1. Obviously, one should be careful in calculating the number of lower pairs, that is P1. So therefore, here n is equal to not 3, 2, because 1 is a higher pair. So 2 plus loop is 1 only, either this side or this side, any one. So 2 plus 1 minus 1. So number of lower pairs is equal to 2. On substituting these values, n is equal to 3, P1 is equal to 2, P2 is equal to 1. One will get F is equal to 1, which is greater than 0. Once again, the mechanism is said to be having a constrained motion with 1 degree of freedom. Then problem number 15, in which the number of links is equal to 3 and number of lower pairs is equal to, here once again, right, 2 and 3 are forming a higher pair. Therefore, number of higher pairs P2 is equal to 1 and remaining are lower pairs, which can be calculated n plus L minus 1. So n is equal to 2, because though it is 3, 1 is a higher pair. Therefore, remaining is 2. 2 plus 1 minus 1 is equal to 2. On substituting, F is equal to 1, which is greater than 0. Hence, the mechanism is said to be having a constrained motion with 1 degree of freedom. Next, problem number 16, in which the number of links are equal to 3, 1, 2, 3, and here 2 and 3. In between there is a point contact, therefore 2, 3 is forming a higher pair. Hence, number of higher pairs is equal to 1. Obviously, number of lower pairs, that is P1 is equal to n plus L minus 1, that is equal to 2 plus 1 minus 1, which is equal to 2. So on finally substituting in equation, we get F is equal to 1, which is greater than 0. Hence, the mechanism is said to be having a constrained motion with 1 degree of freedom. Then taking problem number 17, in which there are totally 6 links, which are named as 1, 2, 3 and so on till 6. And here in between 5 and 6, there is a point contact. Hence, number of higher pairs here equal to 1, that is 5 and 6 is forming a higher pair. Therefore, number of higher pairs is equal to 1 and remaining all are lower pairs, which can be calculated by using n plus L minus 1. So, among the 6, 1 is a higher pair. If I just remove, if I just neglect, then the number of links will be 5 plus number of loops will be 2 here. Therefore, 5 plus 2 minus 1, which is equal to 6. On substituting these values, F is equal to 2, which is greater than 0. Hence, the mechanism is said to be having a constrained motion with the 2 degrees of freedom. Then problem number 18, this is an examination problem in which totally there are 7 links. And here there are no higher pairs at all. Straight away P2 is equal to 0. Because all the pairs are lower pairs in this example, hence n plus L minus 1 to calculate P1, that is equal to number of links are 7 only, because no higher pairs at all, plus number of loops 1, 2, 3 and 4. Therefore, 7 plus 1 minus 1, 7 plus 4 minus 1, which is equal to 10. On substituting n is equal to 7, P1 is equal to 10, P2 is equal to 0. In the equation of degrees of freedom, I will get F is equal to minus 2, which is less than 0. Hence, the mechanism is statically indeterminate structure. Now, one more exam problem is, that is problem number 19, where in this mechanism shown in the figure, one of the two parallel links, because totally here there are AB, CD and EF, three links, in which one of the two parallel links, that is EF or CD, is a redundant link because none of them produces any additional constraint. If any one of the two links is removed, then also motion remains same. Hence, any of the two links is considered while calculating the degrees of freedom. So, here this mechanism is having a redundant degrees of freedom, because whenever the links are parallel to each other, if any one of the link is removed, if any one of the parallel links is removed, then also there is no any other additional constraint. Hence, the given mechanism is having a redundant degrees of freedom. So, thank you. So, today we have discussed about, in the beginning, the inversions of a double slider crank chain, then next Grahoff's law, followed by a simple numericals on it, and what is planar mechanism and how to find the degrees of freedom for a planar mechanism. Then we have solved around about 15 to 20 problems how to find the degrees of freedom for a simple mechanisms, including the problems that have been appeared in the examination. Thank you. In the next class, I am going to begin the straight line mechanisms. Thank you, one and all.